Yeah, how many dimples does a golf ball have? I've always wondered. And obviously in a moment we're going to look at how they're arranged. It's very interesting and there's some unsolved problems involved. But for now, the question is just how many? So we're going to count them. I mean, we could just go through and like mark them off as we count them, or we could actually like number them as we go. So guess we're gonna number them. I'm gonna do the Wilson here, and producer Nicole has volunteered. And so now we're just gonna go through and we're gonna take these and we're gonna number the dimples. Let's get to work. 1, 302, 303 dimples on a golf ball. So if you guessed anywhere near 303, well done. Although we haven't had producer Nicole's number, she's done. What do we got?
331.
331. I'm not going to double check you're working. That is way neater than mine. Good work. So there you go. Golf balls have between 303 and 331, give or take, dimples. But why? Probably maths. It's going to be maths. So why are these different? I mean, from that we can conclude that the act of putting dimples on a golf ball is a non-trivial task, or at least there are choices to be made, because these different manufacturers are like, what, roughly 10% different number of dimples? So there's clearly not one standard way of doing it. Like, there's one standard basketball. They all look roughly the same. There's one standard... I'm not even going to start on that. Look, the point is, golf ball manufacturers have had to make choices, although they're trying to achieve the same thing, an even distribution of dimples on a sphere. And the challenge of arranging points on a sphere so they're evenly spaced is not easy. Here we have a points on a sphere simulator written for me by my friend Christian Lawson Perfect. Currently there's 1 point on a sphere. I can increase the number of points, and what this does is try to maximize the total distance between all of them. So actually, if I go down to 2 points, you'll see that they gradually evolve to be on exactly opposite sides of the sphere. And what we're calling the energy in the system, that's just the sum of the distance between every pair of points. So let's go back up to 4, and they will arrange themselves into a perfect tetrahedron. I can actually turn on the polyhedron. Look at that, regular tetrahedron. This problem of if you want to arrange points on a sphere, what is the arrangement that kind of maximizes their separation is called the Thomson problem, after J.J. Thomson, who discovered the electron. But they had a different model of where the electrons are in the atom compared to our modern understanding. We know they're like in orbitals, which is its own whole thing. Thomson had the pudding model of the atom, where the electrons are just kind of in there. But Thomson realized, because they all repel each other, they will arrange themselves into some kind of shell so that they've maximized the separation between them, which is exactly what we're doing here. Which is why, even though in terms of the physics it was wrong, in terms of the maths doesn't change. Maths is always the same. We still call it the Thomson problem. And Christian's system here has found a solution for 10. So that's how you'd arrange 10 points on a sphere such that you're maximizing the distance between them. And the shape that is there, that's it there. Now you think, how hard can this be? Surely we have nice, neat solutions. Well, there are neat solutions for platonic solids. So if I do 12 and get them to gradually arrange themselves, so what they're doing is they're jiggling around, trying to maximize that energy value up on the top left there. I can actually increase the heat, and that's how much they're jiggling. So if I make them more likely to jiggle, then they're never going to settle into a nice fixed arrangement. But if we don't have enough heat, they'll take forever to get to where they have to be. So there's a balance of how much we're kind of annealing or bumping them around. And then actually I can change how fast the simulation is running, so I can speed it up or slow it down. So let's let them settle into a nice arrangement. I'm going to show the polyhedron. Ah, look at that. It's an icosahedron. So the solution in this case for arranging a number of points on a sphere that matches the vertices of a platonic solid is just that shape. But for a number of points it doesn't happen to match a platonic solid, it's a mess. So for 10, you've got this weird, regular looking, because it's still maximized that distance, but unusual shape. In fact, I printed that shape out. There it is. I'm going to have a closer look at it. That is 10 vertices. As best you can maximize the distance between all pairs, which you can kind of think of as it's trying to make it as regular as possible for some definition of regular, but there's no perfect solution. So it's just kind of gone for good enough is good enough. But here's the problem with the Thomson problem. It actually doesn't solve our golf ball issue. It's solving a different problem. So this is the go-to thing you talk about in terms of arranging points on a sphere, which seems like the golf ball situation. However, you know what? Let me just show you something. This is 20, and a dodecahedron has 20 vertices. So you'd expect this to end up being a perfectly regular dodecahedron. But you give it a second, and guess what? It's not. I'm going to slow down the heat a bit, and I'm going to speed up the simulation just to evolve that in a little bit quicker. You end up with this shape, which is not a dodecahedron. The problem is, it's not just dealing with these edges we can see in the polyhedron. This is what we would call the convex hull. It's the smallest shape that fits around all the points. And because they're all on a sphere, they all end up as vertices on a polyhedron. The actual Thomson problem, because it originates from electrons, is every electron is repelling every other electron. So actually, this point on this side is repelling not just the ones near it, but the ones on the opposite side. So we're actually solving something subtly different than just spacing them out on the surface of the sphere. We care about the points on the other side of the sphere, which is why you don't, even for the platonic solid cases, get a nice, neat solution. In fact, it's a mess. We don't know. It's an unsolved problem. You can have a number of points, and if you want to arrange them on a sphere such that you're maximizing every single pair of points, we don't know. Some of them we know we've got the best case, but there's no general way of doing it. And I did this one as well. That's the one for 29. Very proud of that. Very manual process though. Christian, however, has just turned it into a button and does it all for you. You can just download the STL, and I'll link to this in the description below if you want to have a play, add some points. There you are, the Thomson problem. Very interesting problem, spacing out these points. Famously unsolved, but we do have some cases that are solved, and for the other ones, we can do what Christian has coded here, a numerical solution. We can just gradually evolve it in on a local maximum. Maybe we double check if it's the global maximum by trying some other ones, and then, for all practical purposes, we can solve it. We just can't do it perfect in theory. However, a golf ball doesn't care. Like a dimple on this side doesn't care what the dimples on this side are doing. We just care that locally they're nice and smooth. And so that's a different problem. Conveniently, a maths friend of mine was previously asked to consult but before that, we have to talk about the Grand Tour poster that we currently have decorating the office. I don't think this is good enough anymore. What? I love this poster. I printed it out and got it framed myself. Unbelievable.
Displate is a system where fantastic paintings, illustrations, designs are available on a metal canvas. Some are provided by artists and creators from around the world, and others are officially licensed designs. As you can see here, I picked Rick and Morty, and mounting them with their magnet system is very straightforward and tool-free, completely safe for your walls. You stick a magnet to the wall, you stick the metal to the magnet. Go to displate.com and use the code STANDUP, or click the link in the description and you will get 26% off your first 1 or 2 plates, or 3 or more, 30% off. That's almost a third.
So we can put the original Grand Tour on the wall there, and no one will even notice it's changed, other than it looks way slicker. It does look way slicker. To find out more, check the link in the description. Now, however, back to the golf balls. Conveniently, a maths friend of mine was, a couple of years ago, asked by a golf ball manufacturer if they could advise on the mathematics of where to best put those dimples.
This is my maths friend, Henry Segerman, and one day a golf ball manufacturer saw this article in the New Yorker about a D120 dice Henry had designed, and they thought, this is a person we can ask some golf ball questions.
Robert Van Houwer, who I work with on the Dice Lab, they contacted him, and then we started doing a little bit of consulting with them. They had, questions. How do you design a shape with, evenly spaced dots and lots of them, and what are the options and all that sort of stuff.
And what was your answer?
I think there were a couple of things we were doing. One was we tried the phyllotaxis approach, so the sunflower spiral stuff.
Yep.
That's a nice way of evenly distributing points, relatively nicely evenly distributing points on the sphere, but then you can add as many as you want. But then I think the main focus was the Goldberg polyhedra.
The Goldberg polyhedra are a generalization on this, the classic football or soccer ball, if you're American shape, where you've got your 12 pentagons and then you've got 20 hexagons. And you have to have the 12 pentagons. That's where the curvature comes from. You can't have a ball with all hexagons. It's a whole thing. We're not doing that again now. Link to the campaign below. However, the point is, while you have to have 12 pentagons exactly, there's no real limit on the number of hexagons. You can have way more hexagons.
Yes, the classic football, aka truncated icosahedron, only has 20 hexagons, but check out this one. It's got 30 hexagons. Why don't we use that? Well, these are both examples of something called a Goldberg polyhedron. The one on the left is the 1, 1, and the one on the right is the 2, 0. And they're quite similar. Both their values add to 2, but they do have different geometry, as you can see. And all these images, by the way, straight off Wikipedia. So credit, Wikipedia. Good work. We'll start by looking at the 2, 0, 1, and the reason we give it a value of 2 is because if you start in one pentagon and you want to get to another one that's nearby, first of all you have to cross this edge, that's one edge, then you have to cross this edge, that's 2 edges, a value of 2 to go from one to another. If we had a more complicated one, look at this one, now we have to cross 1, 2, 3 edges. Or check out this one, we got to cross 1, 2, 3, 4 edges. This is a 4, 0. And don't worry about the different colors. They're just different shaped hexagons. They're not all perfectly regular. They've got slightly different edge lengths to make it a sphere. We could have them all the same edge length on the left. That's a, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a 10, 0 Goldberg polyhedron. The one on the right, also a 10, 0, but we've adjusted the length of the edges to make it more spherical. So that's what the different colors represent, just where the edges have been changed. But what does that 0 mean? Well, if we go back to the 1, 1 and we try counting the edge crossings for this, we have 1 to go up, we go up another 1, hang on, we're heading towards the wrong pentagon. We're not going towards one of the closest possible ones. That would involve going over here. But that's a new direction. So we have 1 in one direction and then 1 in a different direction. That's why it's a 1, 1. So this one here is a 2, 3 because if you start in one pentagon and you go 1, 2, 3 edges, change directions, 1, 2, you end up at another closest pentagon. Oh yeah, I did a 3, 2, not a 2, 3. If that upsets you, here you go, 1, 2, 1, 2, 3. You got options. Or you know what? Go back to these two. 1, 2, 3. There you are. You get over there. Or indeed 1, 2, 3. 1, 2. For our purposes, we don't care about the order because you end up on another pentagon. And for the record, there are other types of Goldberg polyhedra. They were all discovered in the early 1900s, but these ones with icosahedral symmetry are the ones we care about for sport balls. And that could be a golf ball, right? Or check out this one, the 4, 3. That looks so golf ball-y.
The big question now is, are these golf balls Goldberg polyhedra? And we will answer that question in a moment. We have some smaller questions to answer first, like, Matt, are you doing any shows soon? The answer is yes. Edinburgh Festival Fringe, Melbourne Comedy Festival. Links below. And why are there even dimples on a golf ball? Like, why not have a golf ball that's perfectly smooth? So I started thinking, I wonder if I could get a perfectly smooth golf ball, like maybe by sanding this or filling it in, and then get someone who plays golf to hit it, and then see if there's a difference. Like, why are there dimples on a golf ball? But then I realized another channel had done exactly that, so I can just ask them how it went.
The fantastic Golf Channel Golficity, who are always up for a challenge, had tried hitting a dimpleless golf ball, and Frank jumped on a call to show it to me.
Can I see the ball again?
Yeah, absolutely. So here she is.
That's incredible.
So what happens is very quickly, it takes off about the same, but very quickly it seems to its momentum dies. So I would say when we were out there hitting it, it travels probably 60% of the distance of a regular golf ball. And right when it feels like it's going to start to reach that apex where it's going to travel a bit, the best way to explain it, it almost feels like it just hits a wall. It's like, it feels like when you're playing into wind right in your face, and it just kind of slows down,
Stops,
dies
and boom.
down. Exactly. Because the slightest, subtlest change in those dimples will cause it to move because of the friction of the air. So, I mean, this is something they've been doing this for like 200 years or whatever it is. They know what dimples do, but they'll do this just as a proof of concept. But the rest of this ball is exactly the same as a regular ball. So we've actually even cut these in half, and all the layering is the same, the weight is the same, and it feels exactly the same. If you closed your eyes hitting a golf ball, you know, with a club, you would never know the difference.
In the video on their channel, they also talk about the history of how golf balls got their dimples.
When they first started playing golf, the very first golfers, the ball was actually smooth. And what they started to notice was that the balls that had been used, the balls that were nicked up and dinged up a bit, were traveling further.
And they talk a bit about the aerodynamics of why the dimples make the ball go further.
It creates they're like little turbulators is the word that I found.
Yep.
And what it does is it just creates those little pockets of air and it reduces drag.
But we're not here to talk about aerodynamics. We're here to talk about the geometry and number of the dimples on the golf ball.
While we've been making this video and producer Nicole's been paying very close attention to everything in the room, she's also counted the dimples on another golf ball. What have we got? It's coming in. Ooh, it's the Callaway. And how many are there?
332.
332. One more than the Bridgestone. Could have missed one of the tiny ones. Okay, so these could be the same for all we know. We really want to know, and I've got one of each of the brands again here. Are these Goldberg Polyhedra? Have they done something different? You know what? At a minimum, I assume they've all got 12 pentagons, because you've got to have 12 pentagons. So I'm going to take, let's do red, and I'm going to find the pentagons on all of these. Here's where we're at. 3 of them we've managed to identify nice, neat patterns, and 2 of them are a nightmare, so we're going to deal with the terrible ones later. Of the ones with patterns, we've got 2 which are a bit unusual. So this one has like a crown and a footer, which are circuits of pentagonal spots, and then the rest of it has got like, not an equator, there's no straight line, but they've kind of then filled in the middle bit with different sized, kind of hexagonal-ish dimples. The Bridgestone has a similar thing where I use blue dots because there's weird tiny divots at the top, and each of them is connected to a irregular pentagon, and there's 3 at the top there and 3 at the bottom there. So they're like weird poles on the ball. And then around the middle, there's this kind of zigzag of pentagons that are linked by kind of the same structure, but I think the way it's evened out is the size of the dimples changes. So there's definitely, in terms of the design, poles, but I suspect the shape of the dimples means that aerodynamically it's very even, but still Bridgestone, that's odd. And Callaway here has clearly an icosahedron. If you color in the individual pentagons, you get the icosahedron structure, so neat, and in between they're very visibly hexagons. So this could be a Goldberg structure. In fact, I can see there's a direct pentagon to pentagon link for each of them. So I'm going to color in some of those hexagons so I can see the structure a bit better, and we'll compare it to some Goldberg Polyhedra. I've colored in some more dots on the Callaway. They're different colors, not because they're different sized faces. It's just because I wanted to alternate so I could count them easier. And this is a Goldberg Polyhedron. This is a 6-0. So that's 6 steps to go from one pentagon to the other one, and 0 because it hits it dead on. So there you are. We can now confirm at least one Callaway manufacturer have used a Goldberg Polyhedron. The other ones are a mess. Some of them are slightly systematic, but they're still all over the shop. And these ones, I don't know what's going on.
over here, these are just ridiculous. And Titleist, that's the one that Golficity visited the factory of and talked about their research. And clearly looking at this, and the other ones, to be honest, apart from the Callaway, has the fingerprint of some kind of numerical solution. So producer Nicole tried to label regions in green, and you can see there is structure to it, but because the dimples don't have to be regular faces, they don't even have to be faces, they can be dimples with weird different shaped voids between them, there's a lot of give. There's a lot of flexibility to exactly alter where the dimples are, how big they are, what the regions between dimples are. So this has definitely been done numerically, and I can imagine they've evolved this over time based on testing in wind tunnels, simulations, robots, actual humans to come up with that pattern. But this pattern is half geometry and half numerical solution. So there you are, golf balls. To answer the actual question, how many holes in one? 300 and something. But it varies, because some golf balls are straight up geometric arrangement, and some clearly have also had a numerical solution, some kind of simulation to optimize them. But thank you so much for watching the video. I had more fun counting dimples than I expected, but I like counting things. I hope you had as much fun watching the video. Huge thanks to Frank from Golficity for helping out. Do check out their channel. I'll link to it below. I'll also link to Henry Segerman's channel, which I think is one of the best maths channels on YouTube. And I mentioned in passing before, I got some shows coming up. If you're in Australia, I'll be at the Melbourne Comedy Festival. I'm hosting 9 Lessons for Melbourne. It's on the 16th of April. So by hosting, I will be on and off the stage all night. It's going to be a great show, some phenomenal guests, most of which we're not allowed to mention yet. Dr. Carl will be there. I always have a lot of fun performing with Dr. Carl, so check it out. I'll hang around afterwards, sign calculators, take selfies, etc. And I will be at the entirety of the Edinburgh Festival Fringe. I'm be doing, oh, it's ridiculous. It's like 25 shows in probably 23 days, but I'll be doing my new show there. It's just me. It's gonna be a lot of fun the entire month. After that, I will be on tour. So late 2025, early 2026, no dates announced for a while, but I will be touring around the UK. Come and see me at the Fringe though.